Hello there, intrepid calculus student. I hope you're doing well as you come to this video, which is going to talk about how to determine the volume of a rotated figure as it is going to rotate around a line, but it's not going to be the X or the Y axis. So in a previous video where I discussed how we can find the volume of a two-dimensional figure as it's rotated around some line, which was either the X or Y axis at the time, where we developed either the disk or the washer method to determine the volume of that object. Now we're going to be doing a pretty much the same type of skill here in this lesson. We're still going to be looking for the volume of an object as it's rotated around a line. However, the line is going to be changing. We're not going to be looking at the X or the Y axis in this case. We're going to be looking at a different type of horizontal or vertical line. Now, just like what we had to do in the with the washer method in the previous lesson that we saw for volume of a figure rotated around a line, we had an outer radius and we had an inner radius. And the way that we determined the volume of a figure at that point is we would say the volume was equal to pi was pulled out as a constant of the integral from a to b, whether you're on the x-axis or the y-axis, we have to have our interval. And then we took the outer radius, squared it, the inner radius, squared it, and then we did our integration. In this case, because I wrote it in r of x, I would do my integration with respect to x here. So this is the same exact thing that we did with the washer method. However, the only thing that's really going to be new is determining where those radii are going to be located, because they're not going to be around the x or the y-axis anymore. We're not going to just be able to count from that line to where the radius should terminate in this case. What we're going to wind up doing is having to go from the line and maybe subtract what the function is going to be from wherever our line is going to be located at that we're rotating around. So let's go ahead and graph this particular function here. We have a square root function, which I'll do here in black, and we're not looking for necessarily any kind of precision. We're just looking for the sketch of the function. So there's the square root function. We have y is equal to 0. So that's essentially just the x-axis here. And we have x is equal to 4. And so I'll just say about here, we'll just say that that's 4. And so the region that we are trying to rotate is this kind of fin shaped here. Okay, that's what we're going to be rotating around. So we need to be able to determine where the outer radius and the inner radius are based on the line that we're going to be rotating around, because we're rotating it around the line y is equal to 4. So here's the line, y is equal to 4. So you can imagine as we rotate around this line, I'm not even going to attempt to draw it because my artistic skills don't allow me that level of immersion, unfortunately. But we're going to take that shape and it's going to rotate it around. So you can kind of imagine that somewhere up here, and we'll just, somewhere up here, nope, I did that the wrong way, didn't I? And it's not symmetric, but we're going to have that thing and it's going to be going around and around and around. Okay, so the distance from the line to, or the distance from the line that we're rotating around to the line y is equal to 0, this is going to be our outer radius. Okay, so the way that we determine what the value of the outer radius is we're going to take the line and we're going to subtract the function that the radius goes to. And in this case, it goes to when y is equal to 0. So I would just say 4 minus 0. So the length of the radius is just 4 in this case. Not bad. Now the inner radius is going to be found by that curved bit of the square root function. That is going to be your inner radius. So we do the same thing. I'm going to take the inner radius and I'm going to subtract that function from the line that we're rotating it around. So in this case, we're rotating around the line y is equal to 4, and I'm going to subtract the square root of x from that. Now, because we're rotating horizontally, we are going to do everything with respect to x. So we, have everything solved in terms of y. The method here, and the method on all of these is going to be the washer method, because we're going to have 2 radii. So I'm going to take the volume formula that we had there, and we're going to just start plugging away. Now, the one thing that I really need to know is what is the interval. So because I'm rotating around a horizontal line, we're doing everything with respect to x, then the interval is going to be on the x-axis, which in this case is going to be from 0 to 4. That's the interval that we're going to be working with. So here I'm going to say the volume is equal to pi times the definite integration from 0 to 4. And of course, I like having that lower bound to be 0. And we're just going to substitute. So the outer radius, in this case, was a 4. So we square it. The inner radius, in this case, was 4 minus the square root of x, quantity squared, dx. And let's just work through it and see what we wind up getting. So pi 0 to 4, this will be a 16 minus in parentheses here, we will get 16 minus 8x plus 1x dx. And you can see here that when we distribute the negative, that negative, the 16s are going to wind up canceling. This will become a positive 8x. And this is supposed to not 8x, it's the 8 square root of x. Wrote that down wrong. 8 square root of x. So that'll become positive, and this will become negative. So we're left with just the integration from 0 to 4 of positive 8 square roots of x minus x dx. So we've simplified the integrand. Now we can go ahead and perform the antiderivative. In this case here, we have the constant of pi, and the antiderivative of 8 times x to the 1/2 power is going to wind up being 16 thirds x to the 3/2 power minus, in here we're going to get a 1/2 x squared evaluated from 0 to 4. And of course, the 0 in this case doesn't really matter because substituting 0 in for x isn't going to change any of its values. Or they all become 0, so they don't really change anything from when we substitute the 4, I should say. So let's go ahead and substitute the 4, and I'm going to say 16 thirds times 4 to the 3/2 power minus 1/2 times 4 squared. And let's think about this for a second. 4 cubed is 64. The square root of that is 8. 8 times 16 is going to be 128 over 3. And then we get 16, and half of that is going to be 8. So we could say that would be 24 over 3 as a common denominator. And subtracting the 24 from the 28 will give me pi. Well, that's 124 minus, or 128 minus 24 is going to be 104 pi over 3 cubic units. And that is the volume that we have for this particular volume rotated around, of the shape rotated around the line y is equal to 4. And that's really all we're doing. This is very similar to the last video that we had for volume with the disc and the washer method. The only difference really is how we identify what the inner and outer radius is going to be of the figure. Other than that, it's all pretty much the same. So let's take a look here. We have two lines that we're going to be rotating, or that we're going to be, or two functions, I should say, that we're going to be graphing. We have the quadratic, 4 minus x squared, so that's going to be something like that. And then the parabola is going to look something like that. So it'll have roots here at -2, 0, at 2, 0, and of course this is at 0, 4. And then we have y is equal to 0, which is just going to be the x-axis here. So the figure that we're going to be rotating is just this stuff here. That's the figure that we're going to be rotating, and we're going to be rotating it around the line y is equal to -1 in this case. So I'm going to be rotating again horizontally. So because I'm rotating horizontally, we want everything in terms of x. So we'll solve our equations for y so that they're done in terms of x. We don't need to really do anything here to that. And we're going to see what's the outer radius and what's the inner radius. So you can see, and I can kind of give just a shadow, I guess, here. We're going to be kind of rotating it around this way, so you can kind of see that the quadratic itself from wherever we are to here, that is going to be your outer radius. And so your inner radius is just going to be from the line that we're rotating around, -1, to the x-axis. That is going to be your inner radius. So the way that we determine those is, in this case, what we did on the last example is we took the line and we substituted our function from the line, and that was because the line that we were rotating it around was above the x-axis. Here in this case, because the line is below the x-axis, we're going to do it the other way around. I'm going to take my function and I'm going to subtract the line that we're rotating it around. So the outer radius is the parabola. So that will be 4 minus x squared minus the line that we're rotating it around, in this case minus -1. So that would work out to be 5 minus x squared. And same thing with the inner radius. This one should be pretty easy to determine. This one we can just count. The outer radius, or the inner radius, is going to be the line of y is equal to 0 minus the line that we're rotating it around, which in this case is -1. And you could just count the distance. In this case, you could just say that it's just going to be a +1. And again, all of these are going to be the washer method because they will have two values for a radius. So again, the volume, pi, the definite integral, a to b, from r of x squared minus little r of x squared dx. And the only thing that I need to know is what's going to be the what's going to be the interval? Now the interval along the x-axis is going to go from, the interval on the x-axis goes from -2 to a +2. But because it's a parabola with no, it's not been shifted horizontally or anything like that, I'm going to do my interval from 0 to 2, and I'm going to double my function. I'm going to use symmetry here, so I'm going to, that way I can get a lower bound of 0, and I will just double whatever the integration is when I do that. So here I'm going to say volume will be equal to 2 pi times the integral from 0 to 2 for big R of x, which would be 5 minus x squared squared minus, in this case, 1 squared. And we're doing it horizontally, so that's in terms of x, dx like that. And let's go ahead and see what we get. Simplify the integrand, and when I expand the binomial, I'm going to get a positive, and I'm going to just write it in kind of standard form here, x squared, and then we'll have a minus 10, nope, I always do that whenever I have something squared. I always still write it squared for some reason. That's x to the 4th minus 10x squared plus 25. I guess I really don't need that parenthesis there. And minus 1, 1 squared is 20. That'll make this a 24. So let's just go ahead and change that to be a 24 when we simplify it. Dx. And now let's just go ahead and do the antiderivative. That's as simplified as the integrand will get at this point. So 2 pi times, and here I'm going to get 1/5 x to the 5th. And then that is going to be negative 10/3 x cubed plus 24x. And we're evaluating it from 0 to 2. So 2 pi, and substitute the 2 now. 1/5, 2 to the 5th, minus 10/3 times 2 cubed, plus 24 times 2. And again, the rest, we're just substituting 0, so technically you can say we're going to subtract 0, but it's, to me, it's not worth doing the substitution for. It's not worth writing that down. And let's see what we get here. So 2 to the 5th power is 32. So that's just going to be 32/5. And then we're going to get 8 times 10, which would be 80. And 80 over 3 doesn't simplify. And then 24 times 2 would be 48. And let's go ahead, we'll just say plus 48 here, because we have to get a common denominator of 15. So get a common denominator of 15. So we have 2 pi. So we have to multiply 32 by 3, which will give me a 96. We got to multiply 80 by 5, which will give me a negative 400. And we have to multiply 48 by 15, which I'm not going to lie, I did that one on a calculator, plus 720 here. And adding all of those numbers up, we get 2 pi times 416 over 15, which works out to be 832 pi over 15. So now let's take a look at a couple of examples where we're going to have things done in terms of y, where we're going to be rotating something vertically. So that's what we're going to be doing here. We have two functions that we're going to be revolving, but in this case, because we're revolving it around the line x is equal to 3, we want to take our expressions, and we want to have these solved in terms of x. So y is equal to x squared. Well, we take the square root of both sides, and it'll give me like a positive or negative square root of y to be equal to x. Y is equal to 4. Well, can't really do much about that one. That's just the other line that we're bounding our function by. So let's see what we have. So here, this is the line x is equal to 3, and the sideways, or the x is equal to the square root of y, that is going to give us something. What am I missing here for the function? Well, the parabola itself, that's just the parent function. Let's just go ahead and look at this as the parent function here. So we have that. And we have the line y is equal to 4. So let's do that one here in yellow. Y is equal to 4. So let's just say that here is 4. So that means we will have points when when y is 4, x is going to be either a positive or negative 2. So this will be at 2, 4. This will be at negative 2, 4. This is at 0, 0. And this is going to be at 0, 4. Now, because we're going to be rotating this one vertically, or around a vertical axis, I should say, this one is going to have an interval on the y-axis, so the interval in this case will be from 0 to 4 on the y-axis. The figure that we're going to be rotating, the shaded bit that we are going to be taking a look at, is really just this whole shape. That's what we're going to be rotating, and you can kind of see that hopefully where the inner and outer radius is going to be. So the inner radius, let's see, you can kind of imagine, we're going to have something over here too, where this bit here and this bit here, those are going to be the inner radius. So that's r of x little 1. And we can kind of see that, let's do green, I guess, that from here, and this one here and this one here, those are going to be the outer radius as we reflect it around the line x is equal to 3. So that is why we want to make sure that we have the positive and negative on the square root. So this side here is going to be the negative square root of y, and this side here will be the positive square root of y, and that is going to help us establish what the inner and outer radius are going to be. Now, what do we subtract from what? In this case, because the line that we're rotating around is, kind of like what we had when the y value is positive. Going back to the first example, we had to subtract the function from the positive line of rotation. Same thing here. I'm going to say the positive line of rotation, 3 in this case, and we will subtract the outer radius of negative square root of y, which would just be 3 plus the square root of y. And for the inner radius, we're going to say 3 minus the square root of y. And again, all of these are going to be the washer method. So let's see what we get here. Again, we're using the same formula, and in this case, because my interval does have a lower bound of 0, That's going to make me happy. I don't have to worry about trying to do any kind of symmetry or anything. So volume is going to be pi times the definite integral, in this case of 0 to 4. The outer radius is going to be 3 plus the square root of y, quantity squared. And then we're going to subtract the inner radius, which would be 3 minus the square root of y. Again, quantity squared, dy in this case. Expand the respective binomials. So the first binomial, the 3 plus the square root of y squared, will give me, in this case, y plus 6 square roots of y plus 9, and I'm just kind of putting it more in standard form, I guess, minus, and then here we're going to have again a positive y minus 6 square roots of y plus 9 dy. Now we can kind of see what's going to happen if I distribute that negative sign in. Here this becomes negative, here this becomes positive, here this becomes negative. So we can kind of see that there's going to be quite a bit of canceling here. The positive y and the negative y here cancel. The positive 9 and the negative 9 here cancel. So the only thing that I have left are 2 positive 6 radical y's. So that will simplify to be pi times definite integral from 0 to 4 of 12 square roots of y dy, or of course you could write that as 12 times y to the 1/2 power if it helps you with your integration. So when we do our integration with either the radical or the exponent, doesn't make a difference, we're going to wind up with, I'm going to pull that constant out. So I'm going to take this constant of 12 out, and all I'm going to do is integrate the radical, or the part that has y. So this will give me 12 pi times, in this case, the antiderivative of y to the 1/2 power will be 2/3 y to the 3 over 2 power, evaluated from 0 to 4. And let's see what we get here. 12 pi, that'll be 2. Well, we can pull out the 2/3 on that one if we wanted to. And that would be 24 over 3, so that'd be 8. Oh, where's my eraser go? So let's pull out the 2/3 also, and go ahead and multiply that by the 12. So if we pull that out, we'll take that 12 pi, and that'll become, so yeah, 24 over 3 is going to give me 8 pi here. Oop, I went to go back to the pink color here. But 8 pi, and then we're going to say 4 to the 3 over 2 power, and 4 to the 3 over 2 power. In this case, that's what, 4 cubed is 64. The square root of 64 is 8, so 8 times 8 pi will be 64 pi cubic units, whatever they happen to be. All right, we got one more to take a look at. And again, feel free to try to go ahead and pause the video and see if you can work any of these out in advance of me. You'll see why. There we go. Get that dotted box gone. So let's see what functions that we have here to graph. So let's look at y is equal to 2 square roots of x. So this one's going to have a bit of a vertical stretch to it. So it's, again, we're just a sketch. We're not trying to get anything specific here. This is the square root, or 2 square roots of x, and then we're going to have the square root of, we just have y is equal to x, which would be kind of something like that. So the bounded region that we have between those is just this bit right here. There's the shaded bit that's going to be rotated around the line x equals -2. So here's our line of rotation, x equals -2, and you can kind of imagine that we're going to have that same kind of odd shape over here. So we can kind of see that here to the square root part, the black curve, that is going to be your inner radius, and from the yellow line to the line of reflection, that's going to be your outer radius. So what I'm going to do is I'm going to take the line of reflection and I'm going to subtract my function from it. In this case, we're going to say, and we want this solved in terms of x. So let's do that real quick. We want this one solved in terms of x. So y is equal to 2 square roots of x. So that'll be 1/2 y equals square root of x. So that'll be y squared over 4 equals x when we square everything, or 1/4 y squared if you prefer. So the outer radius, I'm going to say the line, -2, minus the outer radius was just the line. So that would just be minus y. And the inner radius will be -2 minus y squared over 4. And again, Washer method. So the interval, where's the interval going to be on the x-axis, or yeah, on the y-axis here? Because we're going from 0 to something. So we're at 0, 0. So I'm going up vertically to that point right there. So those points, because of the vertical stretch, the only place those are going to meet is going to be at 4 and 4. So my interval on the y-axis from 0 to 4 is what the interval is going to be. So we're going to say volume is equal to pi times the definite integral of 0 to 4 of the outer radius, which in this case will be -2 minus y, quantity squared, minus the inner radius, -2 minus y to the, nope, not y to the 4th, y squared over 4, quantity squared, dy. Again, I want to expand the binomials and see, will I have anything that can simplify? So expanding the first binomial here, I'm going to get a positive y squared plus a 4y. Oh, oh, no, y'all don't need to see that. Sorry. Y squared. Where is that? Plus 4y plus 4. And if I expand the other one, I'm going to get a y to the 4th over 16 plus a y squared, and then plus a 4 dy. And then we'll distribute the negative again and see what happens here. So if I take that negative and I distribute it, this becomes negative, this becomes negative, and this becomes negative. So the y squareds, I have a I have a positive y squared here and a negative y squared here. Those are going to cancel. I have a positive 4 here and a negative 4 here. Those are going to cancel. So I'll be left with my integration pi from 0 to 4, and I'm going to have 4y minus y to the 4th over 16 dy. So let's see what we wind up getting here when we do our antiderivative. So the first one's not going to be a big deal. The antiderivative of y will be 1/2 y squared, so half of 4 will become 2y squared. Then we're going to have a reciprocal of 1/5 here, so 5 times 16 is going to give me 1/60th y to the 5th power, excuse me. Got something in my throat there. And we're going from 0 to 4. So again, I like having that lower bound to be 0 because it really means we only have to substitute the upper bound. So let's see what we end up with. So I have 2 times 4 squared minus 1/60th times 4 to the 5th, and 16 times 2 will give me a 32, and then 4 to the 5th power, I don't know, I did it on my calculator, 4 to the 5th power divided by 60 works out to be a negative, in this case, 64 fifths. And getting a common denominator here, go down a little bit, of 5 will give me 96 pi over 5 cubic units. And that's really all there is for the material that we have here, where we're looking at the volume of a figure rotated around a line that is not going to be the x or the y axis. So I hope this information did a couple of things. One, I hope it reinforced the idea of what you do for the washer method, how you identify the inner and outer radii, and just give you a little bit more practice with the integration. And that's about it. If you have any questions, guys, feel free to get in touch with me. But thanks for watching. Take care and be good.